I hope everybody can see my screen. So this is the webinar series 2023. This is the third series in this webinar. This is going to be on valve modeling using Simerics and Simerics-MP+. I'm your host today, Dr. Chiran Srinivasan, and I'm joined by my colleague, Dr. Yawei Chan. I am the branch manager in our Novi branch of Simerics, which is the application arm of our Simerics. We are in a suburb of Detroit. And we are very glad that you can make it today to learn about our capabilities for modeling valves in Simerics. So our outline of this presentation is going to be first talking about Simerics CFD. Simerics is a company, then Simerics CFD, a particular focus with the valve application. Then we will demonstrate how to set up a valve and how to simulate this using Simerics. We will take an example of a spool valve, which is a pressure relief valve. Then we'll talk about two different case studies. One case study is a spin-off of this valve demo. We demo this valve and then try to show you how this can be used for getting engineering results. And then the second case study is going to be a thermostat and bypass valve, which is a valve system that is part of a coolant system. And we're talking about how we got pretty good results for such a complicated case. And then we'll talk about the upcoming webinar. And if you have any questions, you can take it at that time. Please feel free to use the chat window. If you have any questions, please type that in there. As it goes, and then we can address them at the end of the session as well. So at Simerics, we have 4 different offices. So our main headquarters is in a suburb of Seattle. The headquarters is actually based in Bellevue in the Washington state. We have this application arm, which I'm heading here out in Detroit in the Michigan area. So we are in Novi. We have an office in Germany and one office in India. So the German one is in Rothenburg, and then the other one in India is in Bangalore. So who we are engineers and researchers. We want to produce path-paving innovative technologies in the world of CAE. So we have done, what we have done so far is we have provided a robust, accurate, fast and automated CAE tools for virtual analysis and design. So there are 4 arms to how we do it, why we are unique, and I want to kind of discuss those a little bit to give you some flavors of why it is that our CFD tool is uniquely placed in producing results that we do. One is the automated meshing capability. So we have our own proprietary binary tree meshing algorithm that automates the mesh generation process. So let's say spaces where you want to resolve the geometry with finer mesh, it automatically decides to resolve that better. And it has an intelligence on its own that can help us automate this process. And it also has the capability to handle complex geometries. So it can essentially, based on the geometric details, it can provide finer mesh in those spaces. So you will have, as a user, you kind of be a little bit at ease on your mind as to how the mesh is getting generated and how it can capture the physics accurately. And also the mesh along with our solver can work very well in tandem, so that can produce quick turnaround, both in preparing the model as well as in terms of running the simulation. The second part of it is our templates. So we have template-driven, user-friendly workflows. So the templates do multiple things. So what they do is they make it easy for any user that is, say, new to the application or new to the software. It's a hand-holding of going through the process setup. And we have templates for several different types of applications. So for pumps, compressors, now we are creating increasingly templates in the automotive industries for vehicle underhood airflow, for fuel tank filling, for piston cooling, etc. So also the templates make it make this learning curve much shorter for users. And so we see that a lot of design engineers can also use the tool quite comfortably without having a very strong CFD background, and that is one of the biggest benefits. Uh, and also it eliminates dependencies on high-end development and manpower resources. For example, we have this general gear template now, which helps create a mesh for planetary gear system. So planetary gear system, as probably you would imagine, is very sophisticated. To create a mesh for that, for a user who is very new, or even for an experienced CFD user, can be very tedious. But using the template, this makes our, it gives you like few inputs that you need to enter, and then it creates the mesh quite nicely, and all the model, say boundary conditions, etc., is set up automatically. And this is what I think makes it very easy for you to use the software. The third part of it is moving domains and dynamics. We can model very complex translation and rotational movements. And we have the template kind of works in tandem with making this movement happen as well. And also we can model leakages and microns sized gaps very accurately. So we can combine it to the bigger regions of the model without losing any fidelity of or any accuracy of the solver. The next part is like a holistic way of thinking about it as to fast, accurate, and robust. The convergence of our different physics that we model, say cavitation, dynamics, or multiphase, or conjugate heat transfer, and that makes it that we are faster, makes it faster for us to compete with other general purpose CFD code. And this has been kind of validated across different industry verticals for several different applications. In terms of Simerics, the overall plan. So we have Simerics CFD, which has been the focus for a while since the inception of the company. So we've developed different flow physics, different physics here. So in terms of physics, we have multiphase, volume of fluid, cavitation, we have heat transfer, we have turbulence. Now we have Simerics integration with Orca 3D, Creo, SolidWorks, CF Turbo, ACES, GTI, Fusion, Rhino, SimScale, NX. So several different integrations. And now we are coming up with our own native FEA and optimization tools. So the FEA solver is mainly focused in coupling because it's written in our it's written by us. It's our own native tool, so we have the abilities to couple it very well with our CFD code, and the same with our optimizer. So now let's talk about this CFD application of valves. So we have several different types of valves that we can model. So we have control valves, release valves, spool valves, ball valves, poppet valves, flip valves, and more. So the templates that we have cover all these valves types. And here we see an array of pictures or animation showing the movements or the physics with which these valves operate, and that we can capture in our numerical simulations. So here we have an example of a spool valve. Here we have an example of this is actually a pump. So you have a piston that is moving up and down. And so the piston itself is modeled like a valve. And then you have the inlet valve and then the outlet valve. So essentially, it's like a 3-valve system you can think about. And so then you have this ball valve in the bottom picture here. You can see a cross-section of different type of ball valve. And then you have a flip valve, which is, for example, in this compressor. So your flip valve is kind of rotational type of valve, basically, that can be modeled as well. So I think in terms of uniqueness, I think what we talk about is we have this wizard type of platform which lets or guides the user to set up the model quite easily. This is essentially like the template workflow. So what it asks it gives specific information of what is needed to create the mesh and set up the model. It also helps automatically assign boundary conditions. Once you provide the inputs there, it knows those are the inputs necessary to carry over to running the simulation. It also has capabilities where we link it to a different dynamics solver. For example, the 6DOF, 1DOF, depending on what you want to solve, and also ability to remesh it so that you can model sophisticated motions. And we can also, use the same mesh to go over a range of motions. So it's not like every time we are creating a new mesh, and that makes our runtime quite quick for these type of applications. We also have the capability to implement a full closure model. So essentially, you can cut off the flow when the valve hits the valve seat, and that is very important or crucial in many applications. Finally, we have specialized outputs that can cater to the different outputs that you want to look for in these types of valves. For example, the forces, the spring force, the preload force, the net fluid forces, pressure force, viscous force, etc. So you can kind of break your valve down into different types of outputs that you will need, and most of them are available ready-made there and processed out. So let me talk about a few of the advantages. In terms of why we think we are very uniquely placed in modeling such applications. So accuracy is paramount in CFD. So you can model several different things, but you want to make sure that at the end your results that you get are is you can make some design changes based on that, or you can use that or take it to the bank, right? So here you're showing an example of a crescent form coupled with a spool valve. And we are comparing 4 different speeds, and we have experimental data, and we have performed the simulations to compare the flow rates of these valves. So essentially, the flow rate that the pump puts out, the valve will regulate it, right? And depending on the location of the valve, the output will, the flow rate will change. So here we have 4 different speeds we are modeling, and you can see the comparisons between the experimental data and the simulations get pretty good comparisons. And I think 2 things that kind of stand out. One is you need to predict the correct force balance of this valve so that you can predict the flow rate accurately. So that involves you being able to capture, for example, this jetting of this velocity quite accurately. Also calculate the resistance there accurately so that you can capture the pressure drop as well as the net displacement of these valves. So all of that is done so that you can get results that that are accurate. So the next one is the ease of model setup. Here I show an example, a snapshot of how you would create a ball valve mesh. As you can see in the left snippet, the template kind of asks you for different things that you will need to provide. Once you provide that, no matter how sophisticated the geometry, all you need to do then is basically enter few parameters. For example, the opening direction, the minimum and maximum gap size that you want to model, and the mesh size, and then it'll create a mesh that is suitable for moving it back and forth. So, for example, this mesh could be squeezed all the way up to 10 micron or 5 micron, and it can go all the way up to 5 millimeter or 10 millimeter. So, and that is done dynamically as the simulation runs. And all you require is few inputs to set up this mesh and start the simulation. The next one is robustly handling like different small gaps and features. Handling small gaps and feature itself is tough, and then doing that robustly is important because you don't want your simulation to every time, or let's say you don't want to babysit the simulation every time. So here we show an example of a pump where you have an inlet valve which opens, takes flow in like a fuel pump, and then it pressurizes by pushing, the piston pushes up, and then it opens the valve, outlet valve. The complication here is multifold, of course, but on that you will notice that we have 4 valves here. So we have 2 valves, the inlet valve and the piston valve, and then you have 2 valves at the outlet which are kind of interacting with each other. There's a ball and a pin. And the gaps here are very, very small, like in the order of a few microns. And between them, as well as between the valve and the valve seat, the gaps are in this small range. And all of this is handled by a solver. So you can see the interactions. You can see the pin kind of hitting the ball a couple of times. So everything is modeled dynamically based on how the pressure in the system behaves and based on the spring constants that this valve experiences. So next is the run times. So doing all that, but also understanding how long it will take to do different things is important. I just show you here an example of this thermostat valve. We'll get into a little bit more details of this thermostat valve later on. So here is the coolant system, right? And you have this thermostat valve, which is controlled by a wax melting mechanism. So you have wax inside, which when it gets hot, gets melted. And due to the expansion, it'll kind of push the spring and open this poppet valve essentially. And then you have this bypass valve, which is controlled by the pressure dynamics. So you have high pressure on the side, it'll kind of open and close this bypass valve. And so what are the different things we are modeling? We are modeling the flow physics, we are modeling the cavitation, we are modeling the heat transfer, we are modeling solid conduction as well. So it's a complete conjugate heat transfer problem. And we need to run this for several hundred seconds. So here we are running for 600 seconds. That's about 10 minutes of physical time. And we can see that for this particular application, it's very quick. We can run this with 72 cores in less than 3 hours, about 2.5 hours. Of course, it's application dependent, but I'm putting together a scenario here where you're modeling a lot of physics with movements that are involved, which are kind of interacting with each other, and that can be done quite substantially fast using the solver and the software. In terms of complicated motions and deformations, we talked about valves. I just show like a kind of a panoramic view of a valve model, like a fuel pump system that we just published this year in the SAE with comments. So what the system involves is you first have like a low pressure pump. This is a crescent pump, which also has a regulating spool valve. And then that connects to a high pressure pump, two high pressure pumps. This high pressure pumps, as we discussed before, is like kind of set of valves operating independent of each other. So you have each pump has three valves essentially. So it's totally 6 valves. And then that high pressure pump system connects to 6 injectors. And we are modeling everything, every single detail, and modeling every single motion of the solid. So that's what I mean by modeling all the solid motions and deformations with accounting for the different physics. So it shows you like the ability to model such a sophisticated system within a reasonable time frame. The final part of this is ability to model cavitation and aeration. In many scenarios, cavitation needs to be modeled, or else your physics that you capture might not be as accurate. Here we show an example of this inlet valve cavitating as it opens up, where it creates the low pressure bubbles, low pressure zones, and it creates the bubbles. And as the pump pressurizes, the bubble collapses, and I think it provides a visualization tool, as well as sometimes you can take the numbers that you get out of here, provide like a characteristic wattage to it, and try to find out if there is potential for erosion damage on some surfaces. Now we'll go to the second part of this session, which is to demo this spool valve. So we are looking at a Poppet valve. So this Poppet valve is something that we work together with one of our Italian universities to publish. The publication is shown here. You have flow coming in the inlet side through the left. It'll go through these 4 holes and then pressurize this chamber. And you have this Poppet valve that is connected together with this deflector, which is kind of the valve spring seat. And it'll open up, relieve the pressure, and it'll go out through these holes to the outlet. And so here, I think in terms of the valve system, multiple things to be considered. So you have 3 different possibilities. One is you have fixed type of grids, you have sliding type of grids, and you have deforming type of grids. So anything that is stationary, right? Like for example, the ports, the outside port is fixed geometry. anything that has relative, let's say a fluid pocket, if it has one side is a fixed object, other side is a moving object, then it's a deforming geometry. For example, this pocket here, if you consider, the left side is a fixed object, fixed solid. The right side is the Poppet solid, which is moving. So when you have relative motion, so one side is held stationary, the other side is moving, then this domain is going to deform. It's going to squeeze and expand. And then we have the third type, which is basically the sliding geometry. Sliding geometry means the both sides are moving. So then there is no relative motion between the two sides. So that means the entire pocket is going to slide back and forth. So that is the third type. So all these three kind of need to be considered to create a valve mesh so that you can optimally provide grid points and move the geometry. So I'll now
action. So here's we always start from the CAD. Here's the CAD, and you can see I'm highlighting the valve the valve part for it. And we start with building the mesh. It's to build the mesh, we have the general measure. So for instance, we start with this inlet port. This is our inlet port. And I just need to select those inlet CAD surface and then put it into the into this box. And then I can directly create the mesh, and it's going to build it. Here I can specify the cell size. Right now I'm using the relative cell size. 0.006 means the cell size, maximum cell size is gonna be 0.6% of the whole geometry. So, and if I quickly show you how the mesh looks like, you can see, so here's the grid. And we have very high quality mesh. Pretty much all the cells, they are square cells. And I can do the same for the outlets. You see, this is my outlet port. And what I need to do is just need to select all the outlets CAD surface and put it here and click this button to generate the mesh. And the outlet, I'm using the same setting. You can, let's say, user has the freedom to change the cell size or do the local refinement and if necessary. So, and you can see we have this inlet and outlet port. If I take a section cut, let's say to show you how the mesh looks like, and here's the section view. You can see majority of the cells, they are it's the box, and aspect ratio is close to 1. And as John said, for some more complicated geometry, for instance, if you have a volume that expands or compress, and that is a valve geometry, we have one a template specifically designed for it. For instance, for this one, we have this for one of the valve geometry, we have this spool valve template, and the user just need to fit in the different categories of surface, and automatically we can build the mesh and specify the boundary conditions as well. For example, and for one of these boundary, you can see as the valve moves, this boundary is gonna compress or expand depending on the valve position. And so we have this, let's say this is our valve surface, which means this surface is gonna move. So we select it and put it here. And we also have this cylinder surface. Cylinder surface basically is gonna expand or compress. And there's also this valve end. Valve end, that is the surface that is stationary, and that is this valve end. And you can see we just need to specify 3 different categories. And then, of course, we need to specify the open direction. In this case, that is in the y direction. I put 0.10 here. And we have this minimum gap size that determines how much we can compress, let's say, the valve, and also the maximum displacement to specify the max movement of this valve surface. And I'll put 1 millimeter for the minimum, and 10 millimeter for the maximum. And I want to mention that this minimum we can also put a closed module. Let's say you put 1 micrometer, we can go as less as micron level. And then we specify the maximum cell size, just like what we did before. Here I put a kind of 2%. And then we can just go ahead and build this valve module. You can see it built another volume. If I show you a section of this volume, you see this is the the volume that we built this with this template measure. So we can, let's say for this is the gap, and this is the other volumes. We can go ahead and build all the different volumes. It's just repeating the process. So to save time, I won't go through all the processes. And but here's the, let's say the volume after we built the mesh. You can see we have a couple of different volume. We have a total of kind of around 10 volumes. And you can see near this liquid zone, I can also use the different mesh setting, different mesh size. So with all the volumes kind of created, the next step is to build the connectivity. For example, we have this inlet, fluid coming in from this inlet port, and then it's gonna enter this cavity, and it will lead through this gap and push the valve open and eventually exit at this outlet. For example, if we look at the this volume, which is this gap, this gap volume is connected with this posterior here, and I mean, usually if you look at the mesh, they have different mesh setting. So I mean, if you build the different volumes separately, you cannot guarantee the mesh is conformal at this connecting region. So that is why we need to connect the interface. For example, for this gap, we have this this bottom one, and this bottom is connected with this volume. So what we do is we select this boundary, and then we go to this volume, and we can select this boundary. And you can right now both boundary they are wall. However, if I click this button, we call it the connect selected boundaries by MGI. MGI is mismatched grid interface, or you can call it magic interface. And what it does is it will connect kind of those two boundaries and create an interface there. For example, this boundary, we don't see it anymore because it becomes interface. And interface means the fluid now, it can pass through this interface and go to the other volume. And if we look at this one, you can see this boundary, part of the boundary becomes interface as well. So we can do, let's say, on the other side, we have the same. The other side, we have this gap, this top boundary, and to connect it, it is connected with this volume, and we can expand it, and so select those together, and then we can create this interface. So you see, kind of we have two interfaces being generated, and we just kind of do the same for the other kind of for the other volumes. And I will not go through all the kind of steps. Basically, we have a total of 8 MGI to be connected, and those 8 MGI, after you connect them, is gonna kind of build the connectivity between different volumes and to allow the fluid to pass through. So here I have this kind of this prepared the mesh with all the MGI being connected. If I show you all the MGI, you can see mainly they are kind of between your different cutting domains. And those MGI then will generate those interface. Those interface will allow the fluid to pass. You can see this one. This one is the basically this one the fluid coming from this inlet, and then it enters the valve domain through those 4 opening holes. And those different MGIs kind of we have a total of 8. Basically, we just follow the same procedure and to build up those different MGIs. So once we have this MGI, we connect different volumes. Next step is to add the solver. And we are solving the fluid dynamics with turbulence. To do it, we go to this model and select these modules. We can click this fluid and add a fluid and also the turbulence. Because we are also solving the dynamics, basically we use we need to calculate the displacement based on the force balance between the fluid pressure force and also the spring force. To do it, we add this kind of translation window. And for this fluid, the spool valve is controlled by this dynamic, by this translation 1 degree of freedom. Fluid turbulence, we can, this if you click, this is just to set up the kind of the solve setting. You can, let's say for time accuracy, the numerical scheme and relaxation, we can change it. And we also have this translation. Translation, let's say, and we can specify the initial displacement of the valve. For instance, in this case, I'll put initial displacement to be 0.0105 and about 1 millimeter. And the body mass of this valve is 0.0178 kilogram. Spring constant is 51,283. There's also a preload force of 377. And moving direction is y direction, and here is kind of the time let's say we ride for 1 cycle, and we can specify the time step size. Let's say for every cycle, if I put 40, it's going to be 40 time step kind of per cycle, basically per oscillation. And let's say we run for 2 cycles. If we run for 2 cycles, let's say basically we are running it for about 7 milliseconds. You will see over 7 milliseconds, this valve is gonna stabilize at a fixed location when it reaches the balance between the fluid force and the spring force. So once we are done with this solver setup, and we go ahead with the material properties. So material properties, to set it up, we just need to select all the volumes, and then let's say the density, and we can put 862. You can also specify, let's say if you have a kind of a density that is function of temperature, whatever, we can use the user defines expressions to define the material properties. And density, let's say, is 0.038. And initial condition, for instance, we can give it a pressure of, for instance, 75 bar or something. So this is the this is the material properties, and then we move ahead with the boundary conditions. Boundary conditions, we have this inlet. And inlet, I'm gonna, let's say we can use volume flow rate boundary condition. I specify the volume flux. It's 45 liter per minute. And we have this outlet port. So outlet port is here, and we can specify outlet to be, for instance, a pressure outlet. I'm gonna use a pressure of 2.5 bar. So this is the pressure kind of the boundary conditions, and pretty much that's it. So lastly, we have a couple of kind of volumes that move together with the valve. Basically, as the valve moves, those volume is gonna do the translation. So those four kind of volumes is very easy to specify the motion. Basically, we just need to go to the volume remesh, specify the volume remesh, and we can use biodynamics. And we can specify this translation window to specify the motion. So basically, kind of that is it. That's it for the setup. And I have a kind of if after we are done, we have this model that is ready to run. And here is the, let's say here's the section view, and this is the grid. And to run it, we just need to come to this simulation and click the start. And after generate all those volumes, you can also check, let's say we have a total of 1.3 million cells. And if you refine it, of course, we're going to get a more kind of more cell counts. And we can go ahead and click right. I'm running it on this workstation with 28 cores. You can see I'm running it on the 28 cores, and running it for three cycles. So we can so this is the residual drop, shows you the velocity, pressure, turbulence, and so different kind of convergence. We can create a different kind of start some post processing. For instance, we want to monitor the let's say the mass balance. What we do is we select this inlet port, and we can monitor the mass flow rates. And we can also select the outlet port and select, and we can create a XY plot. Basically, it's gonna create a plot as a function of time. And we can, let's say here, we can click this mass flux and monitor how the mass flux looks like. You can see of course, we can also add them together to monitor the kind of the net flux. We have inlet, outlet. Ideally, we should get kind of a zero net flux. That indicates we reach a mass balance. You can see that. I mean, we do get a pretty very decent kind of mass balance. So this we can also create a monitor point. Let's say user is interested in the pressure fluctuation or the velocity at different location. And to do it, we can just, let's say, click this button. It's gonna generate a different monitor point. Just like, let's say you are interested in the temperature, you put a thermocouple to monitor temperature. And here we put a point to monitor the run kind of during the simulation. For example, for this point, I can create a plot, and then we can monitor the pressure fluctuation or pressure variation for these points. So, and we have this, let's say, different monitor point being created. And let's say, for instance, we have this one. If I plot the pressure, you can see this is how the pressure changes within this point. And that is for the monitor point. And we can also, let's say, if you select all the volume, we can also plot the pressure contour. This is the pressure contour, shows you from let's say we plot 0 to 50. Basically, we have this high pressure and low pressure at this outlet. If we want to do a section cut, and we can also, let's say, plot velocity magnitude or the pressure contour. For example, if I plot the velocity magnitude, you can see we have this fluid. Right now, we have this thin gap. The fluid coming in, exits through this thin gap and forms a very kind of a high pressure jet. And then the fluid pushes the valve away, and eventually they're going to reach a balancing point. So then you may be interested in, okay, what is the current location of this valve if we use the force balance to monitor it? To plot to know the location, we can just go to this spool valve module. Let's say we click create another plot, and we can monitor the displacement. You can see the displacement, basically it shows you how far this valve is away from this location. Right now it starts from whatever kind of the initial point is about 1 millimeter we specified. And it's gonna, let's say, because we're solving the dynamics, this position keeps changing. Eventually it's gonna, let's say, fluctuate and stabilize around 0.8 to 0.9 millimeter. So that is kind of our outlet is run kind of a little bit longer. So we start at this around 10, 11 and 10 a.m. So it's going to take about 10 minutes to finish. And I will pass kind of the session to Chirans. Chirans can continue, then we can come back and monitor the results. Yeah, Chirans.
So, so we demonstrated how to set up a valve model. So I think pre-processing, you need to extract fluid regions and prepare the model, which regions are moving, stationary, etc. Then you mesh it. Then we create this mismatch grid interface algorithm to connect the different domains together. Then add the different physics that you want to solve, and then add the boundary conditions, and then the fluid properties, which is the volume conditions, and then the simulation is running. So let's talk about these results. Actually, this paper is a very interesting paper. If you are interested, we can pass over this manuscript and you can have a look at it. So what essentially they do is they will, supply flow through here, and they have three different, let's say, cracking pressures that they are interested in. And they're trying to understand the behavior of this deflector, which is kind of the spring seat. And what you can kind of imagine is when the flow comes in through here, it pressurizes this channel. And then I think Yahweh showed in this results, as it's developing, you see a very high speed jet that kind of goes through this very small orifice when it opens valve, and it'll kind of impinge on this deflector surface. And that actually pressurizes this surface. So it creates high pressure on this surface. So the high pressure on this side starts to get balanced with the high pressure on that side, because it's like a one solid system. And I think you will see some results which are very kind of counterintuitive. So let's talk about that. So you have experimental data that they kind of measured, but of course they cannot remove the deflector in the experiment because it happens as a spring seat. But in simulation, you can let your imagination fly, right? So in simulation, the red spots or the black spot is the experiment with the deflector. The simulation results, the red one is with the deflector, and then you have the blue dots or the blue diamonds, which are the simulations without the deflector. So what you notice is, as you have three different cracking pressures, 14 bar, 46 bar, and 75 bar, right? And in the low cracking pressure, you increase the flow rate, and you see without the deflector, as you increase the flow rate, there is quite a lot of increase in the pressure difference. So what it means is you kind of essentially you increase the opening more and more. So your pressure essentially you are kind of increasing the flow rate. So that means you're creating like a delta P gradient across that orifice of this valve, right? But when you add the deflector, you will see that you'll see the pressure drop actually reduces. So what this means is basically that the deflector is actually creating as it's balancing the flow, and it creates a higher pressure on this side. So it kind of opens the valve lesser and lesser as you have this deflector there. So that's why your result starts to kind of deviate. So this green is a deviation from the case for this case with the deflector, without the deflector and with the deflector. And I think, of course, what is apparent is our simulation actually does excellent job of capturing the behavior. And this is true for the three different cracking pressures. And what you notice is, as you increase the cracking pressure, you go to the highest ones at 75 bar, there's actually an overcompensation. So meaning the pressure on the deflector gets large, that it actually overcompensates the pressure. So there is a negative gradient that gets generated across the valve. And actually the simulation does pick that up as well. So there is a slope change, or essentially the change in slope is picked up by the simulation, as well as the change in the behavior. So which is kind of very reassuring in terms of how you want to capture this physics, right? So I think you can see this in this picture here. So this is like kind of the jet that originates through this orifice, through this valve opening, and it impinges on this deflector. And you see the high pressure that gets created on this deflector surface. So you're seeing that the high pressure is 11 bar on this side, and you can see that the pressure here gets very close to that number on this deflector surface. So that starts to kind of throttling this valve. So it's kind of creates lesser and less flow output, which is what you see here. The flow, um, essentially the pressure gets throttled, right? The pressure delta P gets throttled. So that's what you see across this. So, and also the simulation predicts this cavitation bubble that gets generated, which is also something that is uniquely suited for our software, as we can model this cavitation physics quite well. Also, this paper talks about like a versus B study on how the deflector shape is. So let's say there is an angle that you create for this deflector with respect to its base angle. So if you have 0 angle or if you have a 45-degree angle, you will see that at 0 angle, the jet comes in and it just gets washed out. But as you keep increasing the angle, the recirculation can actually accentuate the pressure on this deflector. So as you increase the deflector angle, you will see that the override pressure starts to even go negative at some point, basically. So that is the first example. It's a very interesting and something that gives us a lot of reassurance that the solver does predict the physics or capture the physics quite well. The second one is a case study of this T-stat and a bypass valve that we published with Ford in 2017. So here we have a system, we have a coolant jacket. Essentially, you have a coolant pump that is circulating flow around this coolant system. So you have like 3 arms that come out of this water jacket. One is going to the radiator, which is kind of mimicked with a cooked up porous media system. And then the other one goes to the heater core. Then the third one is bypassing directly back to this valve. So that's the bypass line. So all 3 of them, so this is the heater core line. This is the bypass branch line. And this is the radiator branch line. And all of them go back to this system, which is basically a coupled system of a Poppet valve, inside which there is a wax chamber, paraffin wax chamber, which is kind of controlling this valve movement. So the wax will melt as the temperature on this side increases, and that will cause it to expand. As it expands, it pushes down, and that creates a tension or force on this pin, and that pushes on this valve, and it's a pretty sophisticated mechanism. And so that opens, essentially the amount of volume increase here is proportional to the displacement of this valve. That's the core or essentially the bottom line. And once this opens, you'll see that the radiator, which is coming cold, right? The fluid is coming through the radiator coming cold, and that will kind of come and mix with the hot fluid, and that is how you cool the system down. And we model all this gory details in our model. So I just show you a mesh of a T-stat valve. This is like a T-stat valve. You can see how nicely the mesh opens and closes. So we can model multiple T-stats. We can model multiple bypass valves. All we can do in conjunction as well. So the results here, we are showing like a comparison of the test for this Poppet valve lift with that of simulation. So you can see essentially what is important is 2 things. One is the correct conjugate heat transfer results. So that will essentially capture the wax melting accurately, and that will essentially capture then the Poppet valve motion. So the Poppet valve motion essentially in this T-stat case is essentially like a prescribed motion, right? Because it just depends on heat transfer. The bypass one is a little bit sophisticated. Bypass is based on the spring and the fluid pressure that is acting across it. And of course, I think you can think about it, right? Bypass, they cannot directly measure the displacement, but what you can do is measure, for example, the radiator flow rate. You can measure, for example, the water jacket flow rate. And if your radiator flow rate is matching well, the water jacket flow rate matches well, that means your coolant pump is putting out the right flow. For example, water jacket matches well, that means the coolant pump is putting out the right flow. So that is good, the total flow that it puts out, right? And then basically the radiator branch is matching. So that means your bypass is doing its job. it's being, the simulation is giving good fidelity results or good accurate results so that you can capture this flow rates quite accurately. So this is the second example, and it shows how we can do this sophisticated system by capturing all the details and do it quite accurately. So that brings us to the announcement about the upcoming webinar. So the next one will be on September 6th. That'll be on the topic of that's a Wednesday as well at 10:30 a.m. The topic will be trying to cover some cavitation predictions that can be done using Simerics software. And I'll then open it up to questions. So if you have any comments, any feedback, please feel free to reach us out. My email is cs@simerics.com. Our phone number here is 4248-513-3200 extension 263. Or you can reach Yahweh at yc@simerics.com. His extension is 272.
Yeah, so the simulation has been running for 10 minutes. And right now you can see that we're reaching a stabilized solution. And what I'm showing on this plot, as I showed earlier, that is the displacement of this valve. Basically, the distance from this valve to this seat. And it's stabilized around 0.85 millimeter. And we can also check, let's say, to check the convergence, we can also check the use other parameters. For instance, the pressure. This is the pressure we monitored at at this location. And you can see that the pressure now stabilized as well. And mass balance is always good, and we are getting zero net flux. That means we have a very good mass balance. So this shows you the velocity velocity flow field, and Terence also shows this similar plot in the presentation. Basically, the jet leaks through this opening and impinge this valve and forms this recirculation. So I'll stop here, and
yeah, I think you can keep your screen shared and let me get to
some. Sure. So I want to let's say you can also save if you want to save a piece of image, we can save an image here. If you open it, it shows you this is how the image looks like. We can also create some animations and to do the post processing. So okay, I'll stop it here. So
yeah, I think the first question is for you, Yahweh. So one of our participants is asking, hello, Dr. Chen, can you provide a detailed explanation of how to set the full closure model, how to determine the center point and radius in the parameters? Thank you.
So the full closure model is, if you go to the the spool valve module, we have this. If you click this spool valve, and we have this closure, you can either automatic or you can specify the radial position. Basically, we set a minimum gap size, and in this case, it does not reach this minimum gap size. However, in some cases, let's say if your fluid force is not large enough, let's say the flow rate at the inlet is small and the spring force is high, the spring is gonna push this valve all the way to this seat and close it. We can either, let's say, set up a minimum gap size. For instance, we can make it 1 micrometers, or we can use this closure module to fully close it. And the user set up the radius and center through this dialog.
Yeah, the center will be basically where your valve will hit the valve seat, and then the radius will be the location, yeah, from that center point, basically. Yeah, I hope that's clear. So the next question is, can you talk about how you handle the boundary layer flow and what turbulence models are available? In terms of boundary layer flow, I think we have the option to refine the mesh size on the boundary. So you can do a local refinement on the cell size on the boundary. So your cell on the boundary is much finer than the bulk mesh. and I think one thing to kind of so we have done a lot of different cases, and what we have noticed is I think the way turbulence wall models are modeled with respect to how your meshing works as well as how your solver solves for it with the different parameters is of utmost importance when you talk about turbulence models. We have the K epsilon model. That's what we have. We are implementing few other models which will be in the versions that will be coming out later in this year or early next year. But so far we have not faced a lot of issues in terms of getting good fidelity of results even with just our boundary layer refinement. We have one capability which is we can add like prism cells on the boundaries which can grow out of the boundaries. Essentially you have to add it to the boundaries. So that is a capability in case where we do find some applications we need the boundary layer mesh. In that we use that, but we need to push the cells in a little bit before you grow it so that your size is still maintained, basically. The next question is, in the spool valve example shown, can you also model a spool valve that is not having an ideal one-off but is inclined, leading to collapsing gap? This can be done. We have done this in the past. So it involves us essentially kind of creating like some expressions to model the slant valve, and it's a little bit more sophisticated, which is not covered in our basic valve template, but this is something we have a lot of experience doing. So if it's needed, please let us know. I think Yahweh is showing. Yahweh, you can quickly talk about the previous question. He's showing this boundary layer mesh that we can create. So you can see we can create like very fine cells on the boundaries using this option. So in cases where we need this, we use this option to do it. So the next question is it possible to analyze fluid-borne noise in a valve? Example, whistling. If yes, do you have a short example? Actually, the answer is yes. Also, the answer is very recent. We have not done this a lot. We actually started working on this noise modeling just this year. We have that included in our solver now, and we are getting very promising results. So in terms of valve, we have not tried out a valve case yet, but if there's an example that you want us to model, please feel free to reach out to us and we will do this demo for free, because this is a capability we are testing out and we'll be very, very happy to have a live example to do it with. Yeah. The next question is two-way FSI accounting for cavitation erosion on the FEA side? If yes, how? Cavitation erosion on the FEA side is not accounted yet. It's the FSI is two-way, but it doesn't account for cavitation erosion yet, and that is a capability that we'll need to explore. I think Yahweh just probably it's good to talk about. So you see in the modules now, we have a aeroacoustic model now, acoustic model essentially. So I think it's using the FWH scheme to model the noise. So we're getting good amount of cases that that customers want to validate, and we'll be very happy to look at your case for the valve as well. So the other question is, could it be possible to set a translation rotation 6-DOF for the valve? Yeah, definitely. This is something we can do, and we have done in the past. And yeah, you just need to add the select modules, do the 6-DOF, and essentially then the motion has to be accounted using the valve mesh, basically. Yeah, you have any comments to add for the other questions?
No.
Okay. Yeah, there's a feedback form if you guys would be gracious enough to fill it to see how to improve this further. We are very glad that we have this platform to reach out to you to show our capabilities, and we appreciate the time that you guys are giving to come and listen to our talks, and we'll try to make it as informative as possible based on the feedbacks that you get that we get from you. Yeah, with that, I want to close the session, and thank you again all